introduce the last speaker of the day. This is Daniele Sepe. I'm going to he's very nice, very good lecturer. He'll be talking to us about finding symplectic balls.
So thank you very much. Thank you for turning collectively 180. And thank you to the organizers. I made the point, given that there are so few of you, I wanted to name you personally. Let's see whether I can do it. It's Martin, Tom, Sylvia, Sue, Jordan, and I've spoken to you. Oh, crap. Okay, never mind. Peter, of course. We just spoke. I am, yes. Right. And so I wanted to talk about something that would excite Jonathan, Liat, and Lisa. If I fail, you can fall asleep. It's a great start, huh? Great speaker. Well, so let me set the ground rules. I will only be concentrating on a very specific symplectic manifold, otherwise known as R to n, and I sometimes will think of it as Cn, where the jth symplectic, jth complex coordinate is this one. Okay, so, and I will only have one symplectic form, which is the standard symplectic form. Okay, and so we'll talk about, there'll be a lot of sets in Rn, and every set that I will talk about is open and bounded. Okay, so I will not say that time and again. And also, so if Americans have immunity against the law, Italians can just disregard the law completely. So a ball in line with what Tara said is something that will have a pi, an annoying pi in it, because we have the same friends, pretty much, I think. So, and sometimes I'll be even more annoying. Sometimes I'll just, yes, I think, yeah. Of course, there is a square, and yeah. And because of something that will become apparent soon, I will also sometimes just refer to as a symplectic ball. So the radius will be relevant, only if you want to calculate volume. So I want to start with a question. Yes, the capacity, yeah. I want to start with a question. And the question is to understand a symplectic ball up to the group of symplectomorphisms. So I was told that one should start with bold aims. This is very hard, right? I want to find a symplectic characterization of a ball, essentially. And why is this a good question? Well, I think this is probably the most overstated theorem in symplectic topology. Gromov said that this is an interesting question. So if you give me some subset of the cylinder of a sufficiently small radius, then that has the right volume, you will not be able to find the symplectomorphism that sends it to that. But then, I think it's 2001. So Viterbo in 2001 came up with a conjecture, came up with a conjecture that relates, so there's a conjecture that relates between certain symplectic measurements, so capacities, versus the volume. So it's a very nice paper, and he says, well, I conjecture that certain symplectic capacities are always bounded by the volume. Okay. Now, I forgot to say that this is joint work with Jaron Ostrova and from Vinicius Ramos. And Yaron is so nice that he introduced me to some of these questions, and then he decided to find a counterexample to this conjecture. Yeah. So this is his amazing PhD student has a surname that I don't remember. So this has been disproved. Still, you know, I already sent my abstract by then, so I couldn't change the talk. But in any case, there used to be a conjecture, and this conjecture said that there was some inequality and balls were minimizers for said inequality. Now, the reason why I kept this motivation is that even Yaron believes that it's worthwhile studying this conjecture for reasons that will be apparent in a second. Okay? How are we doing so far? Questions? Okay, so if there are no questions, then I will start. So this is a very hard question because this is very infinite dimensional, right? Take any compactly supported function and you get the symplectomorphism by taking the time one map for its Hamiltonian vector field. So I have to restrict myself, and I restrict myself to a nice class of subsets called Lagrangian products. And so what do? You take, so we'll use notation that is, so you take two subsets, they always satisfy those hypotheses, and then you just take the Q's lying in the first and the P's lying in the second. Okay, so often my subsets will be, well, all of my subsets very soon will be convex, so I will draw convex things. And the times L is because in symplectic topology, if I just write times, sometimes people think of a symplectic product. Okay? And why are these guys interesting? Fundamentally, because one, and this is very interesting, so they're related to billiards. Specifically Minkowski billiards. I don't know if I have time, but if I do at the end, I'll explain it more clearly, but essentially you take the boundary of such a guy. I've drawn it so that the boundary is amenable. These guys can be more complicated. And then you take, this is the contact manifold, so it has a contact form, and then there is a red vector field. And you study the dynamics of that red vector field. And that red vector field will behave like the dynamics of a billiard where the reflection, so this is the billiard table, and the reflection law is determined by this guy. So it's sort of a strange billiard. That's why they have a special name. They're called Minkowski billiards. Again, I'm trying to get somewhere, so, but I want, so Minkowski, yeah. No. So the boundary, so this is, yeah, the boundary is contact. Did I not say boundary? Oh, okay. No, it's fine, it's fine. Okay, but I want the word billiards to stick with you, because I will come back to standard billiards, you know, angle of incidence is the angle of reflection. But then there is something which, so this conjecture does not hold, but for certain Lagrangian products, which are centrally symmetric, meaning that these subsets are symmetric with respect to the origin, if UQ and UP are centrally symmetric, then the Viterbo conjecture implies a conjecture in convex geometry called the Mallet conjecture. And this is work of Arstein, Avidan, Karasev, and Ostrova from, the exact year will come in a second, 2014. So there is, so in spite of the conjecture not being true in general, it's still well studying because it's stronger than a conjecture that's been open for over 100 years. And it's something about volume of certain polytopes. Okay. Right, so I'm going to restrict to Lagrangian products, and I want to tell you what's known, which is not very much. And I'll start with a theorem due, I mean, it's sort of an offhand remark in a paper, so by Lattices, McDuff, and Schlenk in 2013. The nice thing about giving this talk is that I can state theorems where there are only pictures. So the Lagrangian product of a square and its dual is symplectomorphic to a ball. Okay? So let's prove this theorem, and let's prove it as though we were physicists. Okay, so a physical proof. So, well, I told you, I want you to think about billiards. The Minkowski billiard associated to the boundary of this guy, I don't know what it looks like. I don't know if it's integrable. I know pretty much nothing about it. I'll come back to my ignorance at the end. Well, I live with my ignorance, but I will point out more of my ignorance towards the end of the talk. But let's just think of the standard billiard in the square. So you just have a particle and it bounces off. You played snooker? Yeah. And so the billiard in the square is integrable. What does that mean? Well, I can give you conserved quantities. The norm of the components of the momenta are conserved, right? Because you have reflections. And in fact, if you think that there are tori lying around, I mean, now I'm beginning to cheat, then you can convince yourself that in order to calculate the action angle variables, the cycles for the tori project down to, you know, tung tung and tung tung. This is what happens. I mean, you can open up any any paper in physics about quantum billiards in the square, and they will tell you exactly what I said. And so you calculate action variables. So it's the integral over the cycle of, well, these are the sums of the pj, so there's a k here, so let me call this k, pj dqj. And this is constant, and this goes, say, from -1 to 1, so you get twice the length of this. And I mean, it's twice the length, because, and I put the absolute value because, you know, I sort of say it's positive here, then I bounce back, it's negative, but I have to change the sign so it becomes an absolute value. Okay. So now I have, and these action angle variables, I mean, these action variables are global. Why? Because, well, we're doing you know, a sort of heuristic proof. So I have this. I have my map, P1, P2. It has a moment map image. This moment map image looks like a triangle. You just multiply it by 4. It will be a bigger triangle. I think you used mu for the, I will use the same notation. And then, so this is B4. And so, you know, there is a symplectomorphism. Ta-da! This is how you, I mean, this is, if you're a physicist, this is how you prove that these two things are symplectomorphic. Please. Oh, sorry. What did I say? So, I mean, excellent question, and I'll come back to what's happening at the boundary at the very end, because again, I will manifest all of my ignorance. I don't know what's happening at the boundary. But it's an excellent question. So you see that my ball, okay, appropriately, is also open. Yeah, so it's all about the, I mean, I think it's annoying to draw with, so this is not how these guys proved it, because A, this is not a proof, and B, they have more brain power than I do. But this is how Vinicius, Ramos, and I, so in 2019, we proved it essentially doing this in any dimension. So here, think of the cube or the hypercube and its dual, and it's always true that it's symplectomorphic to an appropriate ball. And in order to formalize this is something that I will skip throughout the talk. You have to make this rigorous. So you want to approximate this by a family of integrable systems using an approximation scheme due to Bench and Giannoni, who wrote this paper in 89, I think. 89, yes. Whereas Latchev, McDuff, and Schlenk used ideas of Schlenk's thesis together with a very powerful result due to McDuff that says that the space of symplectic embeddings of a closed ball into an open one is connected. So this is something that's come up time and again in various guises today. Whereas our proof is a very layman's proof. It doesn't use any pseudo-homomorphic curves. But their proof only works in dimension 4, because McDuff's result is a 4-dimensional result. Are there any questions so far? Yes?
So I'm a bit confused. You don't seem to use the Lagrangian product with the dual at all, right? You just pick some axiomatic coordinates.
Correct. In fact, I can prove a lot more. So long as I have something here that has a certain symmetry, I can prove that it corresponds to the preimage of something here under this map. You are perfectly correct, yes. I like when people actually pay attention to what I'm saying. So thank you so much, yes. But you're right, and this, it's a sort of, it's like with my students, they sort of want spoilers. So you've just given a spoiler, I was going to, ta-da! But yeah, never mind. Did I answer your question? Any more questions? So right, so.
Sorry, it's a spiritual question. So the psi here and there, just because you're doing physical proof, can you just take psi as a block sphere, morphism, some transcoping into block sphere?
I don't know what you just block sphere.
A block sphere, as in when you have on a state, you have states on and mapped onto the surface of the sphere. So that normalize everything.
I don't know. It's probably true, and if you read papers in physics, in fact, they may do it that way. I don't know. I'd love to talk to you about this more because I understand nothing about quantum mechanics, or pretty much.
He's just asking you if your transformations are unitary.
No. I mean, at this level, at the level of physical proof, maybe yes, but. The actual symplectomorphism that we get is something that is obtained by a limiting procedure. I mean,
Well, the fact that you have the 4 on the board.
yes, that also, yeah.
But I'm saying I think that's
Thank you so much. I'm sorry if I didn't answer your question.
Oh, you did.
Okay, thank you. Right, so, okay. So this is sort of a warm-up, and it's, I want to state the main theorem that I want to talk about, and then I'll try and convince you that it's actually, well, there's a lot behind it that you have seen, but maybe not in this form. So the motivation for the main theorem that I want to talk about is work of Alexei Balitsky. And so, because of the Viterbo conjecture, people started trying to compute these symplectic capacities to find minimizers, because they wanted to look for balls. And this guy did and said, hey, if I take the equilateral triangle, and I take its Lagrangian product with the regular hexagon, this is a minimizer in Viterbo's conjecture. In fact, he has this is true in higher dimensions. If you take here a regular simplex, and here something called a permutahedron. So that's a beautiful result. And it uses the Minkowski billiards, so work of Yaron and Arstein Avidan to compute these capacities. And so Yaron came to Vinicius and I and said, hi guys, can we prove that these are balls? And yes, so this is what we did. So this Lagrangian product is a ball. And if I can get to where I have to get to, which I doubt, you'll be able to work out the capacity of the ball that I'm referring to, because I have a very specific guy in mind here. Yes?
So Viterbo's conjecture is that certain capacities are bounded below by the volume.
They're a lower bound for the volume times some factor, and yeah. Yeah.
And so when you say a minimizer, you just mean like when that...
Yeah, that's inequality. Yes. Apologies if it wasn't clear. Right, and in fact, soon enough I will leave this four-dimensional world. We have a resulting high dimension, but it only agrees with Balitsky's prediction in dimension 2. We sort of found new minimizers for Viterbo's conjecture, which people didn't know about. So the rest of my time, which I think is 28 minutes and 50-something seconds, is to try and explain to you why you would believe this. Is there a question? You have a question? Huh? Okay. Why you'd expect this guy to appear here and this guy to appear here, and perhaps why you'd believe this. Okay, please.
So in one dimension up, is it tetrahedron times trihedron?
No, one dimension up is, I'll show you what it is, but it is a non-regular simplex times a rhombic dodecahedron. But you look at me like that, but you've seen these guys because they come from Lie theory. And so
in high-dimensional stuff, is that also a ball, or is that so we cried a little bit. We can't get a symplectomorphism because we're not good enough at matrix analysis, but we can get a symplectic equivalence. So they're indistinguishable. If you squeeze this a little bit, you can embed it in here, and if you squeeze this a little bit, you can embed it in there. I'd be happy after the talk to talk about the minutiae of this, especially with you, Alan, because there's something about matrix analysis for symmetric matrices that we could not solve, in case you're interested. I think Eugene used an acronym that I didn't quite understand for idea, but the idea of how we prove this, the too long didn't read sort of thing, is so billiard in the triangle can be approximated by a Toda lattice. So Lie theory comes in. Oh, it's the same. I mean, yeah, it's the same. A more interesting, a slightly different question. I love the fact that I'm asking myself a question, but these things are very they're very specific to the position in which they appear. If you tilt one of them a little bit, sort of goes out of the window. So it's as you saw in Tara's beautiful talk, I mean, these things are very fine. I mean, there's something that which is surprising, at least to me. So right, so let me give you a 3-minute crash course on integrable billiards on regular polygons. I love when people they will appear here. They will appear here. I mean, once I say the magic words, things sort of, which is why I wanted to talk about this, because it's sort of if you don't put it on the right glasses, it feels all a bit mysterious, and with the right glasses, it's like duh. So integrable billiards on rational polygons. So a polygon is rational if every angle, so everything is convex. So a polygon is rational if every angle is a rational multiple of pi. So when is a billiard on a rational polygon integrable? Well, it has to have 3 properties. It has to have a conserved quantity. And in the equilateral triangle, if you think of the momenta as a complex number, so the pair P1, P2 as a complex number, it's the real part of P to the 6th, or the imaginary part of P to the 6th. Because, I mean, just convince yourselves that, I mean, there's the dihedral group has something to do with this. And you think, aha, and this is, you know, when I, when I started working on these things, but how about, you know, any regular polygon should have a conserved quantity. And the problem is what happens at the vertices. So this is where your question, Eugene, sort of comes into play. I mean, it's all fine and jolly to do this up in the air proof, but if you have, so this is meant to be an angle of 2 pi over 3. And here, so the sort of the reflection law is completely well defined in the interior of the edges, but at the vertex, which edge wins, right? And here you have a problem because you have this sort of orbits. So you can't regularize this at the vertex. If you wish, the function that you think is a conserved quantity for a regular, arbitrary regular polygon, the Poisson bracket with, say, the Hamiltonian describing the thing, is sort of a delta function concentrated at that vertex. And what else do I want? Oops, I wanted a different color. I want that the invariant surface is a torus. What do I mean by this? You know, in the standard setting of integrability, the dynamics happens on a torus. Now, what is an invariant surface? Well, think of a polygon. I'll draw an equilateral triangle as best as I can. And now what you do is, if you have the particle, instead of reflecting it, you just reflect the polygon and continue the orbit straight. And you keep on doing this. And if you do it, eventually you get several copies of this guy, and you identify it appropriately. This is motion on a surface, linear motion on a surface. Okay? And I'm saying that this surface has to be topologically a torus. You can get higher dimensional things. Take a regular pentagon. I think you get something. I can't remember. I mean, I can give you the formula to calculate the genus. And there are precisely 4 regular polygons on which billiards are integrable. Can you guess what they are? Huh? Yeah. Correct. The square, the equilateral triangle, so half of the equilateral triangle, and I'll draw it this way. It's half of a square, but it's, so this is meant to be pi over 4. There are reasons why I can do it the other way around. It's just my choices of roots. And as Alan suggested, I'm just going to give them names. And the names are meant to be suggestive, right? They should correspond to root systems. And this is where they come from. So this is the next thing that I'll be talking about. So here. And by the way, that proof sort of dealt with this, and I claim to have proved this, right? So unfortunately, you know, I won't have a punchline saying, oh, I now can do all of them, but that's where I'm going eventually. 20 minutes, okay. Okay. The square times the square as a Lagrangian product is a polydisk. So it becomes the product, the symplectic product of 2 disks. Pretty much by the same argument here. So it replace this. So what this is doing is reflecting in the axis, right? I mean, this map is simply doing that. If you do that with the square, you get a square here. You just expand it, you get a square here, and this will be a polydisk. Okay, so I'm going to assume that you know about root lattices, because time is slipping away from me, and I'm just going to say that, and it's, you know, sort of, so there are root lattices or root systems appear naturally in the study of Lie theory. It's one of the biggest
results in Lie theory, the fact that you can classify complex, semi-simple Lie algebras by pretty much their root systems. I mean, it's one of one of the most astonishing results I understand, which admittedly it's not that many, but never mind. And so what do you do? So let me show you how you obtain these guys, or at least one of these guys. So there is an example, so a root system. So I'm not going to tell you what it is, but I'll be happy to answer a question about that. So an example, so you take, I think I call it Vn, and it's, so these are, I'm sorry if this is familiar to some of you, but I take this hyperplane in Rn plus 1, and then there is a root system that is called An, also, well, and that is given by elements of this form where I is not J. Okay, so this is, well, it should be familiar. And now let me do this thing. Let me do an operation. So if I have a root system, let me define this. So if I have a root system, so root system on a vector, an inner space V, let me call it delta, I will define something that I will call S of delta, and that is, I take all the y's in V. I forgot to mention something, so I can't do this yet, sorry. So for a root system, I can take the root system delta, I will fix simple roots, R1 up to, I don't know, Rk, and then I will take minus the maximal roots. Why? It will become apparent in a second, but I can do this. In this context, these are, so when n is 2, so for n2, in this context, this is just E1 minus E2 and E2 minus E3, and this is E3 minus E1. And once I fix this, I can define an object called S delta, which are the y's in V. So I have on a vector space V with an inner product. I can define this set where J, well, let me call this Rj plus 1, where over all the J, so for all J. So I have a bunch of roots, just a bunch of vectors, and I want to find the ones that have no, that have inner product at most 1 with all of them. If you do this for A1 times A1, you get the square. If you do this for A2, you get the equilateral triangle. If you do this for B2, you get half of the square. And if you do this for G2, you get half of the equilateral triangle. You can check. But it makes sense for any root system. So at least with 17 minutes to go, I made sense of why this guy appears. And now you see, if you do a quick calculation with A3, that the guy that you'd expect here is not regular. I mean, it's just it's a computation. I've given you the ingredients. It may be an ugly computation, but it's there. I recommend using Mathematica for it, because I failed time and again. So how are we doing so far? Are there any questions? No? Okay. So now, I have the billiard in here. I explained to you that it's integrable in some sense, or you believe me that it's integrable. Now I have to tell you why or how it can be approximated by a Toda lattice. At least now I have introduced root systems, and so for those of you who know about generalized Toda systems, this is not that surprising, but it was very surprising to me because most simple things tend to be surprising to me. And so this is a beautiful story that goes back to the 70s. There was a lot of interest in finding integrable systems that arose from nearest particle interaction with exponential interactions. So let me just put some names up. Toda defined them in 67, and then my mathematical grandfather, Bogoyavlensky, generalized them in 76. What's the idea? You have a circle and you have n particles, and so you want to study the dynamics. So I did remember the square here, of where a particle feels only the presence of its neighbors, and the way in which it feels the presence of its neighbors is proportional to the exponential of the distance between these two guys. Okay? And if you fix an alpha positive, you can put an alpha here and an alpha squared there. And these indices, so this sum here in particular, well, only this sum, is meant to be cyclic. If it's not cyclic, we're talking about the non-periodic Toda lattice. But if it's cyclic, and I need it to be cyclic, not because I don't have integrability otherwise, but because I have integrability by connected with compact fibers. So these are integrable. And so the first people to find integrability of these guys were Henon and Flashka in 74. And because I'm a sadist, I guess, I'll give you in the n equals 2 case, so I have 3 particles, I'll give you the integrals in all their glory. One integral is the center of mass. And the second integral is a bit more fun. And in fact, Henon in his paper has the formula for any n. I strongly recommend that you never look at those formulas. But well, this is the energy, right?
That's more or less the same.
This guy is a bit more complicated. I don't know how to understand it, except for if I let alpha go to 0 and I do a change of coordinates, I get precisely what I told you I would get, the real part of p to the 6th. There will be things that will appear and I have to make some changes of coordinates. But I don't know, I mean, it's a great, I will try, Jonathan, to answer your question, because how on earth did this guy come up? I mean, this guy is easy-ish to guess. Exactly. But this guy, and in higher, when n is 4, you get things that are quadratic in the p's, and then the p's start interacting with the q's, and it's a whole mess. And so I'm doing 10 minutes, so that's good. Well, for some definition, good. But before I give you the answer to your question, where did this come from? Let me just say that my mathematical grandfather, so this was defined by Toda, the contribution of Bogoyavlensky is to understand or observe that this guy is precisely exp of QRJ for the RJs that I've displayed up there for you. So he said, how about I just take any irreducible root lattice and I just stick it in, and it's still integrable. And so you get for every irreducible root lattice, irreducible reduced root lattice, you get a different integrable system. And these are called generalized Toda lattices. The ones that we're looking at in this talk are the AN, or specifically the A2 Toda lattice. but because Toda just looked at the A2 case, I will just drop the A2. And right, and the other thing that I wanted to mention is that Flashka's contribution is crucial to this story. He showed that the dynamics of this Hamiltonian can be encoded in a lax pair under a suitable change of coordinates. So once you have lax pairs, you essentially transform the dynamics of this into dynamics on matrices, and then you leverage the fact that these are isospectral flows, and so the eigenvalues or the coefficients of the characteristic polynomial are precisely the, of some matrix, are precisely the constants of motion. And Jonathan, this is how this guy appears. I mean, I could rewrite this and get a matrix, and this is like the coefficient of one of the coefficients. I think it's the constant coefficient in some characteristic polynomial of a matrix. So there is, I mean, it's not physically intuitive, but at least, you know, sort of, I know how to construct all the ones that Henon gets by a simple procedure. And so, right, and so I wanted to mention something that I like a lot. So if I set HC, remember that I have an alpha here. So let me call for a C positive, let me say that this is, what is it? C times, oh yeah. So there's a C here, sorry, there's a C here, exponential of minus C over 2. So my constant alpha is the square of this gadget. Then we can prove, so that the limit as C tends to infinity of HC is equal to the billiard in, well, let me take this off, in S AN. So I told you that one of the ingredients in the story, maybe I erased this, yes I did, was trying to approximate the billiard dynamic in the equilateral triangle by the Toda lattice, and there is, in a suitable sense, you can do it. And this is something that was, in fact, observed. I sort of, there's a lovely book by Kozlov and Treshev from the 90s, in which they sort of hint at this fact, but they don't sit down and prove it. Or maybe they proved it and they thought it wasn't relevant. I don't know. But there is, in a very precise way, I can establish this, this limiting procedure. And then the upshot of this is that, so the upshot is I can use the action angle variables for the Toda lattice to obtain the result. And the global action angle variables for the Toda lattice were obtained, amongst others, by here. So these were obtained by, oh Jesus, yes, is this the right one? Yes. So Flashka and McLaughlin in 76. Van Merbeke, also in 76, and then Henrici and Kappeler in 2008. And let me tell you how this connects to my story, and then I'll be done, hopefully within the next 5 minutes and 30 seconds. So let me try and now give you a heuristic proof of why the triangle times the hexagon is a ball. So I have some integrable system, a family thereof. So I have some integrable system that I'll denote, I don't know, by phi c. So for each c, I have an integrable system. I'm letting c go to infinity. And I have some moment map image. This moment map image is complicated. Let me call it BC. Then I have global action angle variables. global action angle variable. So let me kill this. So I don't know what they're called. Chi c, and I have a psi c, and you can check. I mean, this is what we do. You check that essentially these on slightly smaller hexagons, they give you, so the image of something slightly smaller lies in a non-precise way like that. Okay, so we try and take an exhaustion of these guys. And we can do it for a discrete set of values, and then we have to do a limiting procedure. But the limiting procedure is only possible because we can leverage a McDuff's result in dimension 4. In higher dimensions, if I have something that is symmetric under the Weil group here, I get a symplectic equivalent. So if I shrink this, it can be embedded into its image and vice versa. So if I have something very symmetric here, so if I have something very symmetric, I can give you a picture description of this. So I take, the sort of ideal moment map, which we call rho, takes, the Weil group here is acting by reflecting in these hyperplanes. And so you take a fundamental domain there, and then you just straighten it out by some map that I can write explicitly. And so if you have the required symmetry, you can find something here, and then you have this symplectic equivalence. I know I'm sort of rambling on, but I'm sort of running out of time, so I can't give you the details of this. However, let me just finish by illustrating how the regular hexagon appears intrinsically just by knowing the root lattice without any reference to the triangle. And this is something that I learned in a book by Conway and Sloan, a great book on lattices. And that's the following. So if I have a root system, delta, so I'll leave it there, you can construct, you can consider the Voronoi cell of delta, and that is the set of y that are y is closer to 0 than to any other root. And if you play this game for these root lattices, you will get, so I'll put them down here, you can see, right? So here you get the dual, here you get this guy, here you get again this guy, and here you get again this guy. No. Exactly. So I wanted to get to this, so it's just like, this is as explicit as they come. And the Voronoi cell of A3 is otherwise known as the rhombic dodecahedron. So I have a minute and a half, so I can tell you what we're interested in for further work. So there is a natural conjecture here. I have an S delta and a Voronoi cell of delta. I want to prove that the Lagrangian product of for any simple irreducible root lattice, not necessarily irreducible, Voronoi, be of the appropriate dimension. Okay? This should be obtained by leveraging the integrability of the Toda of the generalized Toda systems. So this is one question. Another question is the boundary. So this is all, in spite of my pictures, I'm only dealing with things in the interior. There is some rep dynamics on the boundary, and here I have rep dynamics on the boundary of this, which is a nice integrable flow. In what sense are these things, if they are related? We expect that maybe some C0 symplectic topology will come in. I just said 3 words that I know absolutely nothing about, but there is a question for people that are more quantum than I am. So the quantum pictures are, if you read about the quantum picture for the square, it's immediate. I mean, they sort of take it for granted. I mean, this symplectomorphism, they say, yeah, it's true. And you're like, why? So I don't know how to do this, but I think there is a nice story there. And given that I am 15 seconds over time, I think I should again wish you a very, very happy birthday. I hope this present was okay. And thank you all for your attention.